All right, example 12.11. I want to estimate the change in a function from 3 dimensions to 1 dimension as I travel 0.1 unit from one point towards another point. So I don't necessarily end up at this point. I just know I travel from this point towards that point, but just because I go in that direction, I'm only going 0.1. So maybe I don't end up there. Maybe I just end up here. So because you don't know your terminal x and your terminal y, right? You don't know where you end up. It's advised not to use the total differential, where you could do the derivative of the function, or the differential of the function is equal to the travel in the x times the derivative in the x plus derivative y, travel in y, plus derivative z, travel in z. But you don't know these points, right? You don't know how far you go in that direction, or rather, you know how far, you don't know where you end up though. So here, let's not use that form. Let's instead use the form given to us in this theorem here. So the differential of a function. So I'm traveling in a certain direction. So let's use our directional derivative. It's the directional derivative times ds, or the amount that we traveled. Right. Now, when you find a directional derivative, we'll find it like we typically do in practice, not with the limit definition, but by taking our gradient vector and projecting it onto the right direction. So I'm going to replace this directional derivative with the gradient of f dotted with the correct direction. Okay, let's figure out this direction first. So I'm going from this point to this point. So the actual vector that points me from our initial point to our terminal point is 2, 1, minus 2. So the unit vector that points me in that direction, remember, anytime you use a directional derivative, it has to be a unit vector. The unit vector that points me in that right direction is 2/3, a positive 1/3, and a minus 2/3. We've bad threes. Okay. So if we find our gradient vector is y times cosine x, right? That's the partial derivative of the f function in the x direction. The partial derivative in the y direction is sine x plus 2z, and the partial derivative in the z direction is a 2y. We're going to dot this with the unit vector, u. So 2/3, 1/3, and minus 2/3. And I'm going to take this, right? That's just my directional derivative. And I'm going to multiply by how far I'm traveling in that direction. I'm going to multiply by this ds. All right. So when we go through this, let's evaluate our gradient vector at our initial point 0, 1, 0, right? Because that's where we're starting at. So that's where we're establishing the tangent line, or the tangent plane. So this gives us a gradient vector. If I evaluate this gradient vector at the point 0, 1, 0, I get 1, 0, 2, which I will project onto the right direction, 2/3, 1/3, and minus 2/3. And then we can tell ourselves how far we're traveling in that direction. We're traveling 0.1 units. So going through this, we end up at, what do we get? Minus 2/3, right? That's the result of this dot product, times a 0.1, So if we approximate, minus 0.067. So this function here changes or drops down approximately minus 0.067 units as I travel 0.1 unit in the direction from this point to that point.